Okay, we're back with another rendition of Quadratics in Quarantine. So we're going to continue graphing. So this is 4.4b. Just a bit of a review from yesterday. So starting off with an equation in vertex form. If we were to graph the transformations, we start off first of all with our basic y equals x squared vertex. So 0, 0. Over 1, up 1, over 2, up 4, over 3, up 9. And likewise on the other side. And we have our original parabola. The first thing we do is we graph the stretch or compression. We have a stretch of 3 here. So what this means is instead of going over 1 and up 1, we're going to go over 1 and up 3. Instead of going over 2 up 4, over 2 and up 12. So 4, 8, 12. We're stretching it by 3. And likewise, we will do the same on the other side. And so it appears that it's getting skinnier, but it's actually getting pulled upwards. So all these points are getting stretched upwards by a value of 3. So that's our first transformation. Our second transformation would be a reflection down. If we had a negative 3, we don't, so we can skip the reflection down. Our third transformation is going to be dealing with the h, and the h tells us here that we go 2 to the left. So we can either move all these points over 2 to the left. So this would move over 2 to, or this one would move over to the left, this would move over to the left. Or, as I prefer to do, I prefer to draw in my vertex and then just draw the points off of that. So that would be an over 1, up 4, over 2, up 12, and the same thing on the other side of our axis of symmetry. And we get our second transformation. Our third transformation is our k, negative 4. This tells us that everything shifts down 4 spots. So from here, once again, we can shift all the points down 4 or anchor it off of our vertex. I'm going to go over 1, up 3, over 2, up, I forget what our value is, 12. And then we have the same points on the other side. So there is our third transformation. Our vertex, as you can see here, is at negative 2, negative 4. Of course, we can take that right from here. Reminder once again, that is the opposite of the sign that you see. Our axis of symmetry, it runs right here, and it's crossing at negative 2. Once again, that is our h value. Our stretch or compression value, that is 3. Our direction of opening, of course, we're opening up, and because this is a plus 3, that tells us that it's up. Our x values, and they're going to be any real number. And our y value, any points above negative 4. So y is equal to or greater than negative 4. All right. If you are given a parabola with a vertex at negative 1, negative 2, opening downwards, and a stretch of 3, what would the equation be? So our equation, of course, in vertex form is y equals a x minus h squared plus k. If we have a vertical stretch of 3, we would sub that in for 3. If we're opening downwards, that would be a minus 3. And as far as our vertex, if it's minus 1, then if we're putting in a -1 for the h, and negative make a positive, it's going to appear here as an x plus 1 squared. And our k value is going to be -2. So there we go. We have taken that information, we can put it straight into equation form. So a second example here, let's say it has a vertex at 1, 5. Let's say it's opening upwards, and it has a compression factor of 1/2. So in this case, we have let's switch colors here, y is equal to a compression factor of 1/2, so that's our A. It's going to be a positive A because we're opening upwards. Our H is 1, so that's going to be a -1. And our K value is 5. If it helps you out, you can, at the side, come up with this information ahead of time. +1 and a +5, and then just remember when you put this in, it shows up in a negative form. So that is that. Continuing on. All right. In this case, example number 3, I'm giving you a parabola, and its vertex is at -2, -1. So here's its vertex, and we're going to go over 1, down 1, over 2, down 4, and here is our parabola. So what I want you to do here is list the transformations in the order you would apply them. So the first thing that we deal with is the A. And I can see that this does not have a stretch to it because it's an over 1. And if we want to look at it this way, it's an over 1, up 1, over 2, up 4. That's our basic y equals x squared parabola. So I know that there is no stretch or compression. So I don't have to deal with that. The second thing I do would be my reflection. So we know that this reflects down. The third thing is we look at our left-right, our h value, and we can see that this translates to spaces left. So from the vertex here, where it originally was with our original, so we've reflected down, and we've gone 2 spaces left, and the fourth would be our K, and it translates 1 unit down. And I probably, instead of spaces, should write the word unit. So we're always dealing with A first, then our H, then our K. Let's try that again with another example here. So let's say this is at 1, 1. And 2, 3. So what are the transformations that we have made in this case? So first of all, dealing with our A, do we have any stretch or compression? And we do have a stretch or compression. We can see that instead of going over 1 and up 1, we are going over 1 and up 2. So that tells us that we have a stretch of 2. We've doubled it. And do we reflect down? Are we opening up downwards? The answer is no. For our H value, we do move 1 space So we translate 1 unit. In this case, we're going right. And our third thing, we're going to talk about the K. And in this case, it translates 1 unit up. So translates 1 unit up. Cool. Hope you all have that. All right, continuing to move on. In this case, determine the equation for the parabola with a vertex at 2, 6 and passes through, don't tell the English teachers I did that, 5, 3. All right, so I don't need to draw this out, but I'm just going to draw a little thing to refer to. So we know we have a vertex here at 2, 6. And we know it's passing through this point, 5, 3. So is our vertex, is it probably going to be like this? Is it going to be like this? Is it going to be stretched? Is it going to be compressed? So we have to figure that out. Now, rather than trying to graph this all out and see if where these points are, I'm going to show you how we are going to do this. So first of all, in vertex form, we have our formula. And let's sub in what we know. We know that our h here is 2. And that's a +2, but the negative +2 would make that a negative. And we know our K is 6. So what we don't know here is our A value. We don't know what our stretch or compress is, and we don't know if it opens up or down. But what we're going to do here is we're going to solve. We actually have one other piece of information. We know that we go through 5, 3. So we can sub that point in. X is 5 and Y is 3. And now we can solve this. So 3 is equal to A. 5 minus 2 is 3 squared plus 6. 3 equals A. 3 squared is 9 plus 6. Now in this case, I'm just going to rewrite this here because that's 8 times 9 or 9A plus 6. And we can start to solve. So 3, move that over, becomes a minus 6 equals 9A. 3 minus 6 is negative 3 equals 9A. A would be negative 3 over 9. A is negative 1/3 in lowest terms. So that tells us that our A is negative 1/3. It has a compression value of 1/3, and we're opening downwards. So if we want to put that, write that out nice and neat, we have negative 1/3 x minus 2 squared plus 6. So there is the equation with this information. I guess if we graphed it over here, it would be opening downwards and it would be compressed by 1/3, so it would appear to be wider. All right, we're getting there. Use a little bit more paper this time. I'm trying to do it a little bit bigger for you. I don't know if that makes a difference on what device you're using and your ability to zoom in. So example 4. So we have a path of a football. And it's modeled by the equation of the height is equal to negative 1/4 d minus 12 squared plus 36. So right off the bat, hopefully you are beginning to see that when you throw a football, it gets thrown like that, up in the air, and eventually comes back down. That's a parabola open downwards. So I expected to see this negative 1/4. A normal parabola is kind of like this. This is we're not throwing the ball almost straight up in the air and back down. You know, if we're throwing it downfield, I would expect that this has been compressed. So to see a fraction there makes sense. So, and our x and our y have been subbed out, and we're using distance and height. So, first of all, if we were to sketch the path, one thing that we can do, and we haven't spent a lot of time doing this, is our t-table. So we have on our x side here, that's our distance, and on our y side would be our height. Now, zero is always a great place to begin. So at 0, what would the height be? So we can literally sub that in. So height is equal to that. Our distance is 0, so sub in 0 for the d, minus 12 squared plus 36. You do that, 0 minus 12 is minus 12 squared, multiply it by that, and then add that on, and you're gonna get a value of 0. Picking another random number here, distance, I'm not gonna go up by ones. Chances are I'm not throwing this ball 5 feet or kicking it 5 feet. So I'm gonna do 6 here next. Once again, if I go through that, 6 minus 12, so subbing in 6 for our distance, we get an answer of 27. I'm gonna do another multiple of 6 here. If I run that through, only here have 12 minus 12, we're gonna get an answer of 36. 18 feet, same thing, I'm just not writing it all out to save some time. John Carl gets upset with long videos. And we'd get an answer of 27. And if I go to 24 feet, blah, 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 it actually hits the ground. So we can graph that. We have all positive numbers, so we only need the positive quadrant of our Cartesian plane, and we have the height in meters, distance 0, 6, 12, 18, 24, and we have our heights, which looks like it can go up to at least 36 here. So, I don't know, 5, 10, 15, 20, 25, 30, 35, 40. All right, so 0, 0, 6, 27, 12, 36, 18, 27, and 24, 0. So we have a parabola that looks like that. What was the maximum height of the football? It looks like here that it is, graphing, it looks like it's at 36, but let's not go by the graph. So the maximum height. Let's look at our equation that we're given. We know that the maximum height is also the vertex in this case. And we know the vertex is at HK. So in this case, our maximum or our vertex is going to be at 12, 12, 36. And we know the first letter here is our distance, our x. This is our height. It's asking for maximum height. So maximum height equals 36 meters. Hope you are all having as much fun at home as I am right now. Part C. What is the horizontal distance when this occurs. So what that's asking is, how far has a ball gone horizontally when it reaches its peak? So we know that that's actually going to be, I guess, our axis of symmetry. We know that when it's at its peak, when it's at 36 meters, it is 12 meters. Here's a question for you. How high is the ball at 10 meters? So at 10 meters here, how high is that ball? And we are not going to read it off the graph. That's not accurate. That could be 34 point something, 35, I don't know. So we are going to use our formula. So our formula is h equals -1/4. Distance, I'm going to put in 10 for the distance. Minus 12 squared plus 36. -1/4, that's going to be -2 squared plus 36. -2 times -2 is +4. When you multiply that out by a -1/4, you're going to get -1 plus 36. So remember, in BEDMAS, you do this multiplication before that. And we get a height of 35. Quick check, that's an answer that makes sense here. We expected it to be in the 30 to 35 range. If you are getting, let's say you had not done the negative here properly, and you got +1, so 1 plus 36 is 37, you know that wouldn't make sense because the ball only went up 36. So sometimes the best check you can do is just, does it make sense? And one other question here. Find another horizontal distance when the height is the same as in part D. All right, so obviously we have an axis of symmetry right here. So we are going to have the corresponding, at 35, we're going to have a corresponding point over here. In this case, we know that this is at 10, which is 2 away from the axis of symmetry. The axis of symmetry tells us both sides are congruent. So if we go 2 over here, we know it will be at the same height at a vertical distance of 14. So we know that our vertical distance of 14 meters as well. So there we go, a little bit of fun with quadratics. Hopefully it's starting to sink in a little bit. Hopefully this formula is starting to make sense. I think this is much like linear equations back in grade 9. When I first started to teach that, I get a lot of blank stares. It kind of doesn't make sense. And we're talking about slope, and we're talking about b values and all this other nonsense. And then all of a sudden it clicks and you're like, this is easy. I'm just running an equation. And you can start to visualize it in your head. You know, with y equals mx plus b, the greater the m, the steeper the line. As soon as you see a b value, you know that that line shifts up. If it's a negative b, it shifts down. If you see a negative m value, you know it's a negative slope. And your brain just starts to process it. Hopefully this kicks in for you or clicks for you as well, and that you just start to see the different parts of the equation and you can start to visualize what that parabola looks like. So right away, opening downwards, wider than normal, vertex is up at 1236. So from the, it shifted on our Cartesian plane. That tells me that it shifted over right and it shifted up. And I can begin to visualize that. So that's that. Do your homework. If you have any questions, please don't hesitate to contact me, and I will draw you up something. I'll write out a solution, whatever it might be, and send it right off to you. All right, everyone. Have a great day.